Welcome to today's problem walkthrough. In this session, we'll tackle LeetCode problem number 109, convert sorted list to binary search tree. We'll explore how to transform a sorted, singly linked list into a height-balanced binary search tree. Let's dive in and break the problem down step by step. Here, we are tasked with converting a sorted singly linked list into a height-balanced binary search tree, or BST. A height-balanced BST ensures that the depth of the left and right subtrees of every node differs by no more than 1. The input is a singly linked list, where each node holds an integer value, and the elements are sorted in ascending order. Our goal is to produce the root node of the BST, maintaining the height-balanced property. This means that the tree will be structured in such a way that it is as balanced as possible, with nodes distributed evenly across its levels. To better understand the problem, let's look at an example. If the input linked list is -10, -3, 0, 5, 9, one possible height-balanced BST representation would have 0 as the root node. The left subtree of 0 contains -3, which itself has -10 as its left child. On the right subtree of 0, we have 9 as the child, with 5 as its left child. This arrangement ensures the tree is height-balanced, as the depths of the left and right subtrees at each node differ by no more than 1. Additionally, the in-order traversal of this BST would yield the original sorted sequence of the linked list. Now, consider a simpler example where the input linked list is empty. In this case, there are no elements to construct a tree, so the output is simply an empty tree, represented as an empty array. This illustrates that when the input list has no nodes, the corresponding BST will also have no nodes. This is a critical edge case to handle in our solution, as the algorithm must account for scenarios where there is no data to process. In another example, if the input linked list contains just 2 nodes, 1, 3, one possible BST would have 3 as the root, with 1 as its left child. This structure maintains the height-balanced property, as the depth difference between the left and right subtrees of the root is 0. It's important to note that there can be multiple valid BSTs for a given input, but all must adhere to the rules of being height-balanced and preserving the in-order sequence of the input. When solving this problem, there are several constraints to keep in mind. The number of nodes in the linked list can range from 0 to 10,000, so the algorithm must be efficient to handle large inputs without exceeding time or space limits. Each node's value lies between -100,000 and 100,000, and the input list is guaranteed to be sorted in ascending order. Key edge cases include handling an empty list, where the output should be an empty tree, and a single node input, which produces a BST with just the root node. By carefully considering these constraints and edge cases, we can ensure our solution is robust and performs well across all scenarios. When approaching the problem of converting a sorted singly linked list into a height-balanced binary search tree, one of the first strategies to consider is the brute force method. The intuition here is to leverage the fact that the linked list is sorted. By converting the list into an array, we gain direct access to each element using indices. This allows us to recursively divide the array into left and right parts around the middle element, which will serve as the root of the BST. The steps are straightforward. First, traverse the linked list and store its elements in an array. Then, use the middle element of the array to construct the root node, and recursively build the left and right subtrees from the remaining elements. In terms of complexity, the time required is O(n) for the conversion to an array and another O(n) to build the BST, resulting in a total time complexity of O(n). However, the space complexity is also O(n) due to the storage required for the array. While this approach is simple to implement, it comes with a memory trade-off, making it less optimal for scenarios where space efficiency is crucial. Another approach to solve this problem more efficiently is the in-place construction method using the slow and fast pointer technique. Here, instead of converting the linked list into an array, we directly identify the middle node of the list, which acts as the root of the BST. This is achieved by using 2 pointers, a slow pointer that moves 1 step at a time and a fast pointer that moves 2 steps at a time. When the fast pointer reaches the end of the list, the slow pointer will be at the middle node. This middle node is then used as the root, and the left and right parts of the list are recursively divided to construct the left and right subtrees. The time complexity of this approach is O(n) log n, as finding the middle node requires O(n) for each recursive call, and there are log n levels of recursion in a balanced tree. The space complexity is O log n, which comes from the recursion stack. While this method eliminates the need for extra storage, the slightly higher time complexity compared to the array-based approach is a trade-off to consider. The most efficient strategy for solving this problem is the in-order simulation approach, which reduces the time complexity to O(n). The key insight here is that we can simulate an in-order traversal of the BST while traversing the linked list sequentially. This eliminates the need for random access or multiple passes. The process begins by determining the size of the linked list, which helps define the bounds for recursion. Using a helper function, we construct the BST by processing the left subtree within the bounds, creating the root node using the current list node, and moving the pointer to the next node to process the right subtree. Each node is processed exactly once, which is why the time complexity is O(n). The space complexity remains O log n due to the recursion stack. This approach is optimal in both time and space, but it requires careful handling of pointers and recursion to ensure correctness. Despite the slightly increased implementation complexity, it is the best choice for large input sizes. The in-order simulation approach stands out as the preferred solution due to its optimal time complexity of O(n) and minimal space usage of O log n. A key realization that makes this approach so efficient is that the linked list can be traversed sequentially while simultaneously constructing the BST in an in-order manner. This eliminates the need for additional storage or multiple passes, which are required by other methods. Compared to the alternatives, the array-based method, while straightforward, uses extra space for the array. The slow and fast pointer method avoids this extra space but has a higher time complexity of O(n) log n. The in-order simulation method combines the best aspects of both optimal time complexity, minimal space usage, and no additional storage. While it is slightly more complex to implement, this trade-off is justified by its superior performance, especially for large datasets. Overall, this approach strikes the perfect balance between clarity and efficiency, making it the most suitable solution for converting a sorted linked list into a height-balanced BST. The problem we're solving here is to convert a sorted singly linked list into a height-balanced binary search tree, or BST. A height-balanced BST is one where the depths of the two subtrees of every node differ by at most 1. Since our input is a sorted linked list, the goal is to preserve this order while ensuring the tree remains height-balanced. To achieve this, we use a recursive in-order simulation approach. The intuition behind this method is that the middle element of the linked list naturally becomes the root of the BST. The left half of the list forms the left subtree, while the right half forms the right subtree. By recursively dividing the list into halves, we can construct the BST in a structured, top-down manner. Instead of transforming the list into an array, we simulate this process using a pointer, which makes the approach both time-efficient and memory-efficient. The first step in this process is determining the length of the linked list, which lays the foundation for simulating in-order traversal bounds. Once we have the length, we define a helper function, buildTree, that will recursively construct the BST based on a given range of indices. To construct the BST recursively, we define a few key steps. First, we handle the base case. If the start index exceeds the end index, it means we've reached the end of a branch, so we return null. Next, we calculate the middle index using mid equals start plus end // 2. This middle element will serve as the root of the current subtree. Before we assign the root, we recursively construct the left subtree by processing the range from start to mid 1. After the left subtree is built, we assign the current node of the linked list, tracked by a pointer, as the root. We then advance the pointer to the next node in the linked list. With the root established, we move on to recursively construct the right subtree by processing the range from mid plus 1 to end. Once both the left and right subtrees have been constructed, we return the root node to complete the subtree. To tie everything together, we use a wrapper function, sortedList to BST, which calculates the length of the linked list, initializes the pointer at the head, and calls the buildTree function with the range from 0 to n1 to construct the entire BST. The reason we use a recursive in-order simulation approach is that it allows us to construct the BST in the correct order while maintaining efficiency. By simulating in-order traversal, we ensure that the middle element of the list becomes the root at each step, which naturally preserves the order of elements. This approach eliminates the need for random access or additional memory allocation, making it very space efficient. Additionally, the use of a pointer to traverse the linked list sequentially avoids the inefficiency of repeatedly finding the middle element, which would otherwise take O(n) time per recursion level. This optimization significantly reduces the overall time complexity. The recursive division of the list into halves also guarantees that the resulting tree remains height balanced. By consistently placing the middle element as the root, we ensure that the depths of the left and right subtrees differ by at most 1. The input data structure is a singly linked list, which provides sorted elements, and the output is a binary tree where each node contains a value, a left child pointer, and a right child pointer. This algorithm achieves a time complexity of O(n), because each node in the linked list is visited exactly once. The pointer moves sequentially through the list, ensuring that no element is revisited. The space complexity is O log n, which corresponds to the depth of the recursion stack. Since the tree is height balanced, the maximum depth of the stack is proportional to the logarithm of the number of nodes in the tree. Let's consider an example to make this clearer. Suppose the input linked list is 1, 2, 3, 4, 5, 6, 7. The output is a height balanced BST with 4 as the root. The left subtree contains the elements 1, 2, 3, and the right subtree contains 5, 6, 7. The structure of the tree ensures that it remains height balanced, with the in-order traversal of the tree matching the sequence of the linked list. To construct the BST step by step, we start with the entire list 1, 2, 3, 4, 5, 6, 7. The middle element, 4, becomes the root. For the left subtree, we process the sublist 1, 2, 3. The middle of this sublist is 2, which becomes the left child of 4. Next, we process the sublist 1, making 1 the left child of 2, and 3, making 3 the right child of 2. For the right subtree, we process the sublist 5, 6, 7. The middle element, 6, becomes the right child of 4. We then process 5, making 5 the left child of 6, and 7, making 7 the right child of 6. This recursive process ensures that the final BST is height balanced and that the in-order traversal of the tree matches the order of the linked list. To solve the problem of converting a sorted linked list into a height-balanced binary search tree, we start by defining the basic building blocks. First, we have the list node class, which represents nodes in our linked list, and the tree node class, which represents nodes in our binary search tree. The list node class contains a value and a pointer to the next node, while the tree node class includes a value along with pointers to the left and right child nodes. Next, within the solution class, we define the main function sortedList to BST. This function uses a helper function called findMiddle to locate the middle node of a given portion of the linked list. The middle node serves as the root of the binary search tree for that range. To find this middle node, we use 2 pointers, slow and fast. The slow pointer moves 1 step at a time, while the fast pointer moves 2 steps. This ensures that when the fast pointer reaches the end, the slow pointer is at the middle of the list. Finally, we prepare for the recursive construction of the tree by defining the buildBST function, which will use this middle node to create the tree structure. The buildBST function begins by checking if the left and right pointers have met, which would indicate that there are no nodes left to process in this segment of the list. In that case, the function simply returns none, meaning no tree node will be created. Otherwise, we call the findMiddle function to locate the middle node of the current segment. This middle node becomes the root of the current subtree, so we create a new tree node using its value. To construct the left and right subtrees, we make recursive calls to buildBST. For the left subtree, we pass the range from left to mid, and for the right subtree, we pass the range from mid next to right. This effectively splits the list into 2 halves, with the middle node excluded, and ensures that the binary search tree is built in a balanced manner. Once both subtrees are constructed, we link them to their parent node and return the root of the subtree. Finally, the sortedList to BST function kicks off this process by calling buildBST with the entire list as input, and the completed tree is returned as the output. Here, we begin by defining 2 essential classes, list node and tree node. The list node class represents a node in the singly linked list, where each node contains an integer value and a reference to the next node. Similarly, the tree node class represents a node in the binary search tree, with an integer value and references to the left and right child nodes. Both classes include constructors to initialize their respective values and set child references to null by default. Next, in the solution class, we define a helper method called findMiddle. This method will identify the middle node of the linked list, which is a critical step in converting the list into a balanced binary search tree. Notice how we declare two pointers, slow and fast. These will help us traverse the list efficiently. The findMiddle method uses a two-pointer approach to locate the middle node. The slow pointer advances one step at a time, while the fast pointer moves two steps. This ensures that when the fast pointer reaches the end of the list or hits the boundary defined by the right parameter, the slow pointer will be at the middle node. This node will later serve as the root of our binary search tree. Moving on, we define the buildBST method, which is a recursive function that constructs the tree. The base case here is straightforward. If the left pointer equals the right pointer, we return null, signifying that there are no nodes to process in this segment of the list. Otherwise, we use the findMiddle method to identify the middle node, which becomes the root of the current subtree. We then recursively build the left subtree using the portion of the list before the middle node and the right subtree using the portion after it. Finally, we implement the sorted list to BST method, which serves as the entry point for the entire process. This method accepts the head of the linked list as input and calls the buildBST method with the head as the left boundary and null as the right boundary. By doing this, we initiate the recursive process to construct the balanced binary search tree. The buildBST method ensures that the tree remains height balanced by consistently choosing the middle node of each sublist as the root. The resulting tree structure preserves the in-order traversal property, where the values in the tree correspond to the sorted order of the linked list. This completes the implementation, providing an efficient solution to convert a sorted linked list into a balanced binary search tree. To begin, we are given a sorted linked list containing the values 1, 2, 3. Our goal is to convert this into a height-balanced binary search tree. The process starts with the sorted list to BST function, which delegates the task to a helper function called buildBST. The initial call to buildBST specifies the range of the list to be processed, with the left pointer set to the head of the list, which is 1, and the right pointer set to none. The first step in buildBST is to identify the middle node of the current range using the findMiddle function. Here, both the slow and fast pointers start at the first node, which is 1. As the fast pointer moves 2 steps at a time and the slow pointer moves 1 step, the slow pointer eventually stops at 2 while the fast pointer reaches the end of the list. This makes 2 the middle node of the current range, and we create a new tree node with the value 2. This node will serve as the root of our BST. From here, we move to build the left subtree with the range defined by left equals 1 and right equals 2, and the right subtree with left equals 3 and right equals none. The left subtree of the root node, which has the value 2, is constructed next. This involves a recursive call to buildBST with the range left equals 1 and right equals 2. Once again, the findMiddle function is used to locate the middle node. Here, both the slow and fast pointers start at 1. Since the range contains only one element, the middle node is directly identified as 1. A tree node is created with the value 1. At this point, we attempt to construct the left and right subtrees for this node, but both calls to buildBST hit the base case and return none, as there are no elements left to process. This makes the node with value 1 a leaf node and the left child of the root node 2. Next, we focus on building the right subtree for the root node 2. The range for this subtree is defined by left equals 3 and right equals none. Since this range contains only one node, the middle node is 3. A tree node is created with the value 3, and both its left and right subtrees return none due to the base case. This makes the node with value 3 the right child of the root node 2. At this point, we have successfully constructed the BST for the first example. The final tree structure is as follows. The root node 2 has a left child 1 and a right child 3. Now, let's consider a more complex example with the sorted linked list 1, 2, 3, 4, 5. The sorted list to BST function again calls the buildBST helper with left pointing to the head of the list, which is 1, and right set to none. To determine the root of the tree, the findMiddle function identifies the middle node of the range. Starting with slow equals 1 and fast equals 1, the pointers move through the list. Slow progresses to 2, then 3, while fast advances to 3, then 5. When the fast pointer reaches the end, the slow pointer is at 3, making it the middle node. A tree node is created with the value 3, which becomes the root of the BST. The left subtree is built with the range left equals 1 and right equals 3, and the right subtree is built with left equals 4 and right equals none. For the left subtree, the middle node of the range, 1, 2, 3, is determined to be 2. A tree node with value 2 is created. Its left child is the node 1, as determined by the base case, and it has no right child. For the right subtree, the middle node of the range, 4, 5, is 5. A tree node with value 5 is created, with the left child being 4 and no right child. The final BST structure for this example is as follows. The root node 3 has a left child 2 with its own left child 1, and a right child 5 with its own left child 4. To analyze the time complexity of our solution, we need to break it down into the key operations involved in converting the sorted linked list into a height-balanced binary search tree. First, let's consider the find middle function, which identifies the middle node of the linked list between the left and right pointers. This is done using a two-pointer approach, where the slow pointer moves one step at a time, and the fast pointer moves 2 steps at a time. The complexity of this traversal is proportional to the distance between the left and right pointers in each recursive call, which we denote as n_k for the kth call. Next, we analyze the recursive construction of the tree in the build BST function. For each recursive call, the find middle operation takes n_k, and the list is then divided into 2 halves, left and right, for further recursive processing. This gives us the recurrence relation for the time complexity, t, n, equals 2t, n/2, plus o, n, where the o, n, term accounts for the traversal to find the middle node at each level. Using the master theorem for divide and conquer algorithms, this recurrence simplifies to o, n log n, which represents the total time complexity of the solution. Now, let's examine the space complexity. The algorithm uses recursion to construct the BST, and the maximum depth of the recursion corresponds to the height of the tree. Since the BST is height balanced, the height is O log n, making the recursive call stack space complexity O log n. Additionally, the algorithm does not allocate memory for any auxiliary data structures. Each tree node is created in constant O1 space, and no extra memory is required. As a result, the total space complexity is dominated by the recursive call stack, leading to O log n. When analyzing best, average, and worst-case scenarios, the time complexity is consistently O n log n, due to the consistent divide-and-conquer approach, and the space complexity remains O log n, given the predictable depth of the recursion. If we compare this optimized approach to a naive solution, the differences become clear. A brute force method might involve converting the linked list into an array, which would take O n time. Using the array, you could achieve O log n, lookup for the middle element, but the overall time complexity of the tree construction would still be O n log n. However, this approach would require O n extra space to store the array, whereas our optimized solution avoids such overhead by constructing the BST directly from the linked list. This makes it more space efficient with O log n space complexity due to the recursive call stack. Finally, we can mathematically verify the O n log n time complexity. At each level of recursion, the total cost is O n, and this remains consistent for all log n levels of the recursion. Summing the costs across all levels gives us O n log n as the total time complexity, confirming the efficiency of our approach. One of the most common mistakes when solving this problem is failing to maintain the balance of the binary search tree. Remember, the goal is to create a height-balanced tree, where the depth of the two subtrees of any node never differs by more than 1. If you always insert the middle node as the root without carefully dividing the list, you may inadvertently create a skewed tree, which defeats the purpose of the balance requirement. Another frequent issue involves inefficient list traversal. For instance, if you repeatedly iterate through the list to find the middle element, this can lead to an O n squared time complexity, which is far from optimal. To avoid this, aim for a solution that processes the list in a single traversal. Errors in recursion are also common, particularly when base cases are not well defined. Forgetting to handle scenarios like an empty list or a single node list can lead to infinite recursion or incorrectly constructed trees. Additionally, modifying the input list is something to watch out for. This may conflict with the problem constraints and produce unintended side effects. Finally, edge cases like a one-node list, a two-node list, or even very large inputs are often overlooked. Testing against these scenarios is crucial to ensure your solution is robust and bug-free. Now, when it comes to interview scenarios, the divide and conquer approach is key. This method involves recursively splitting the list at its midpoint to build the tree, ensuring O(n) time complexity and maintaining the required balance. Mastery of pointer manipulation is also essential, especially for efficiently splitting the list using the slow and fast pointer technique. During interviews, it's important to articulate why you chose a particular approach. For example, you might compare converting the list to an array versus solving it in place with recursion, and explain the trade-offs in terms of memory usage and complexity. Since recursion can be challenging under pressure, practicing similar problems will help you build confidence. Related problems can also strengthen your understanding. For instance, convert sorted array to binary search tree is a simpler variation that uses arrays. Middle of the linked list is directly applicable since finding the middle node is a key subproblem. Merge two sorted lists helps reinforce linked list traversal and manipulation skills, while flatten a multilevel doubly linked list builds your understanding of recursive tree-like structures. These problems are excellent practice for refining your skills and preparing for variations. There are also alternative approaches to consider, each with its own trade-offs. One option is the brute force method of converting the linked list to an array. This simplifies traversal and indexing since arrays allow random access, but it comes at the cost of O(n) extra space. This method is straightforward to implement but sacrifices memory efficiency. A more optimal approach is in-place recursion using slow and fast pointers. This method avoids converting the list to an array and directly processes the linked list. By finding the middle element with pointers and recursively dividing the list, you achieve O(1) extra space usage. However, this approach requires more careful pointer manipulation and can be tricky to implement correctly. Another possibility is an iterative approach using a stack to simulate recursion. While less common, this avoids potential recursion depth issues, which can be a concern for deeply nested recursive calls. That said, the iterative approach often results in more complex code and is harder to debug. Each of these methods has its strengths and weaknesses, so choosing the right one depends on the constraints of the problem and your familiarity with the techniques. Great work! To recap, we successfully converted a sorted linked list into a height-balanced BST using a divide and conquer approach. Remember, mastering problems like these enhances both your algorithmic thinking and your understanding of data structures. Thanks for joining me today, and I'll see you in the next walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!